Hi, welcome all to this new reading group session organized by ContinualAI. Today we have the pleasure to host Gido Van from the Baylor College of Medicine, who is going to talk about his recent work, Class-Incremental Learning with Generative Classifiers. And I think this is a very nice concept of trying to merge discriminative models with generative models. And this, I think, can shed like new insights about how tackling class incremental settings, which we know are more complicated than other settings in continual learning, in a very original way, I would say. So thank you again, Guido, for accepting my invitation, and feel free to start your own talk at this point. Thanks.
Yeah, well, thank you for the invitation. I'm really excited to present this recent paper, indeed on class incremental learning with generative classifiers, and it's joint work with Ju Lee and Andreas Tolias. And well, before I start, I should say I'm very happy for any questions to just be asked like during the presentation as well. So please feel free to raise your hand or just interrupt me at any point. And also, before I start, I would like to say that I think that this paper is kind of a bit different than, say, the average deep learning paper, because the main goal of this paper was certainly not to propose a new method that obtains some state-of-the-art performance on some benchmark. Even though I will show some, well, what I think are new state-of-the-art results. So if you're interested in those, it's still worth to stay and listen. But I think really the main contribution, or the main point of this paper is more conceptual, in the sense that it describes and motivates a new, or at least so far overlooked strategy for incrementally learning new classes. Okay, so that's maybe a bit of a claim. So let's start and see whether you agree. Yeah. Okay. But first, it's important to really be explicit about what exactly the problem is that we're trying to address in this paper, because it's not enough to simply say that the problem we're trying to address is continual or incremental learning with deep neural networks. And the reason for this is that there are these three, I would argue, fundamentally different types of continual learning, which each come with their own challenges and which therefore require different types of solutions or approaches. So very briefly, the first type of continual learning is what I would call task incremental learning, in which an algorithm must incrementally learn a set of clearly distinct tasks. And the defining characteristic of task incremental learning is that it is always clear to the algorithm which specific task must be performed, which actually means that in this scenario it's actually easy or almost trivial to prevent catastrophic forgetting, because we can actually just train a different network for each task to be learned. And that will become important later in the presentation. So the challenge with task incremental learning is therefore not, or at least in my opinion, it should not be to solve catastrophic forgetting, but it should be to find ways to efficiently share parts of the different networks to achieve positive transfer between the tasks, or efficiency in terms of parameter budget. Okay, then the second type of continual learning is what I call a domain incremental learning, in which an algorithm must repeatedly learn the same type of task, but with changing context or in different domains. And in this scenario, preventing catastrophic forgetting is indeed an important challenge, because preventing forgetting is just simply by design is no longer possible. But well, this type of continual learning is actually a bit less relevant for this paper, but well, I wanted to mention it for completeness. So, and then the third type of continual learning is class incremental learning, in which an algorithm must incrementally learn to distinguish between a steadily growing number of classes. And well, as Vincenzo already mentioned, this class incremental learning is generally considered to be kind of the most challenging type of continual learning, and this is the kind of problem that this presentation is about. Okay, so let's have a let's start by having a better look at what exactly at what exactly it is that that is challenging with class incremental learning. And well, the challenge really is that the algorithm must learn to distinguish between classes that are not actually observed at the same time. And well, to get a better feeling for why this is so challenging, let's have a look at this this toy example here with different classes taken from the OmniCloud dataset. So now imagine that in the first learning episode, we observe these two classes on the left. And now if we have an effective deep learning algorithm, this algorithm might for example learn the rule that if an image has more than two of these small circles, then it's that image belongs to class 1, and otherwise that image belongs to class 2. And well, that's a very effective rule, and that's basically what we would in kind of the current deep learning setting. That's what we would want the algorithm to learn. But then in the second learning episode, say the next day, we now observe these two classes on the right. And now, if the only thing that we retained from the previous learning episode is this decision rule based on the small circles, then well, you can hopefully see that if that's the only thing we retained, we won't really be able anymore to learn effective rules to distinguish between class 2 and class 3, or also between other pairs of classes. So that is, for class incremental learning, we really need a special strategy. And so well, let's start with, okay, what kind of strategies are already out there? What kind of strategies are people in the continual learning literature currently using to address this problem? So probably the most common and probably also the most effective strategy is to store some subset of past data in a memory buffer, and then, for example, revisit or replay that data later when we encounter new classes. And well, it's quite easy to see why this approach would work, and indeed, in practice, it turns out to be very effective, even with surprisingly small memory buffers. But of course, like storing data might not always be possible or desirable, and therefore, in this paper, we actually we only focus on approaches that do not store data. Okay, so when storing data is not possible, and sort of an alternative strategy, which kind of mimics the strategy of storing past data, is to learn a generative model to generate the data to be replayed. And with such generative replay, there's sort of like different variants. Like one option is to kind of just replay generated samples at the input level, and this works very well for problems like MNIST. But then when we go to more complex problems, that turns out to be actually rather complicated to really replay at the input level. But then a couple of papers have shown that actually, if instead you replay higher level feature representations generated by your model, then that could also work with more complex inputs. And yeah, so even though this generative replay has been shown to be effective for class incremental learning, a very important an important disadvantage of this strategy is that it makes training relatively expensive, because essentially the algorithm is constantly being retrained on all previously seen classes. And so recently, therefore, there's been sort of a surge in interest in developing so-called replay-free or rehearsal-free approaches for continual learning. And one such rehearsal-free approach is parameter regularization, the third strategy here. But although in theory this strategy is suitable for class incremental learning, in practice it has been shown that at least by itself, this strategy does not work very well. But nevertheless, we included some methods, sort of for completeness. And then another rehearsal-free method another rehearsal-free kind of approach or strategy for class-incremental learning is what I like to refer to as bias correction. And so this strategy, what it does is that it essentially it tries firstly it starts by observing that a softmax-based classifier incrementally trained on new classes is very heavily biased towards the more recently seen classes. What this strategy does is it tries to remove this bias essentially by ensuring somehow that the magnitude of the output weights of all of the classes in the softmax output layer is comparable between the different tasks or between the different classes. And yeah, here on the right are listed a few methods for which I think the main strategy is some sort of bias correction. And well, I should say that for bias correction, but actually also for the other two methods, like I of course couldn't include all of the methods that use this particular strategy, so I chose some methods I'm familiar with or that I think are representative. And well, my expectation is that other methods using similar these strategies their performance should follow similar patterns as the ones that I'm about to show. But if in your experience they don't, I'd be very interested to hear about it. Okay, so this are the current strategy. So what sort of strategy are we proposing for class incremental learning? But well, first again, some very brief background. So as I kind of already alluded to, in deep learning, the kind of the default approach to classification is to learn a discriminative classifier. For example, a softmax-based classifier is an example of a discriminative classifier. And so informally, this type of classifiers, they aim to directly learn rules or shortcuts or features in order to distinguish between the classes that it is confronted with. And but also within the class incremental learning literature, so far the default approach has been to try to learn such discriminative classifiers. But actually, from a class incremental learning perspective, sort of an important, or I would say a critical disadvantage of these discriminative classifiers is that what they do is that they perform the comparison. So they really learn the rule to distinguish between the classes. So they do the comparison between the classes to be learned during training. And from a class incremental learning perspective, this is problematic because the different classes to be learned are actually not observed together during training. Okay, so the alternative is to learn a generative classifier. And well, what a generative classifier does is essentially that it first learns a generative model, which you could also think of as sort of a template or a representation for each class to be learned, and then at inference time or at classification at test time, it performs classification based on Bayes' rule, which you could think of as based on some sort of similarity measure, if you want. And so from a class incremental learning perspective, the attractive aspect of this approach to classification is that the comparison between classes is no longer during training when the classes are actually not observed together, but the comparison is taking place during inference, or during the classification decision itself. So we kind of avoid this this problem altogether. Okay, and then on this next slide, I try to describe these discriminative and generative approaches to classification a bit more formal in a bit more detail, and I also try to kind of rephrase the advantage of the generative classifier in a slightly different way. So a discriminative classifier aims to directly learn the conditional distribution of y given x. But with class incremental learning, this is problematic because, well, based on the most recently seen data, the empirical version of this conditional distribution is indeed heavily biased towards the most recently seen classes, or the last few classes. And so now the approach for class incremental learning that we propose is to instead aim to learn the joint distribution over x and y and factorized in this way, and then classify using Bayes' rule. And so the advantage of this approach is that with class incremental learning, the empirical version of this distribution, it's really like these distributions, right? There's essentially a separate distribution for each y. These distributions, they should not have any particular bias in the class incremental learning setting. While at the same time learning the marginal distribution over y is typically quite straightforward. For example, we could simply count the number of times each class is observed, or in many situations, it's also reasonable to, for example, assume like a uniform distribution over all classes, which is actually what we did in this paper. Okay, and then finally, another way to phrase the benefit of the generative classification approach is to say that it essentially turns a challenging class incremental learning problem into a much easier addressable task incremental learning problem, whereby each task to be learned consists of learning a class conditional generative model for a specific class. Okay, so that was the more conceptual part and I would say the conceptual argument of the paper. But of course, it still remains to be demonstrated that this generative approach that we argue in favor of could indeed have benefits for class incremental learning. And sort of in order to show that with kind of the simplest possible, or well, not maybe the simplest, but with a simple example, sort of a proof of principle, we used the implementation described on this slide. So what we did, we trained a separate variational autoencoder model for each class to be learned. And then during inference, we used importance sampling to estimate for each possible class the class conditional likelihood of the test sample to be classified. And well, essentially what this implementation does is that it builds upon the insight that a naive approach to the task incremental learning problem is to simply learn a separate network for each task. So that's basically we use the insight that generative classification turns a class incremental learning problem into a task incremental learning problem, and then we sort of use the most naive approach to solve this task incremental learning problem. And well, I should make one remark, because kind of the danger with this approach is that it could lead to very large models with very large parameter budgets. So well, to ensure a fair comparison, it's important to say that we made sure that always the total number of parameters of our VAE models was similar to the number of parameters used by the comparable generative replay approaches. Okay, so then on what type of benchmarks did we test this approach, or this implementation? So well, the benchmarks are kind of summarized in this table on the bottom, but I kind of wanted to highlight sort of like three important aspects, which I think are very important differences between sort of like class incremental learning benchmarks used in different papers. So the first one is this, well, what I refer to as task-based versus task-free. So a task-based protocol for class incremental learning essentially says that, okay, we divide it's sort of split MNIST, right? Like we divide the 10 MNIST digits to be learned in tasks or episodes of 2 digits, and then we first observe all the zeros and ones, then all the 2s and 3s, etc. And task-free essentially, there's no such task-based structure, but we observe all of the digits to be learned according to some arbitrary class incremental learning sequence. And well, it has been argued that this task-free continual class incremental learning is a lot harder than the task-based version, and in practice that is true for many methods, in the sense that many of the existing methods that I mentioned or listed on a few slides ago are indeed not able or not directly applicable to this task-free protocol. But at the same time, I would argue there's actually not really an inherent that this setting is inherently more difficult than this one.
Sorry, Guido, can I ask you like a quick question?
Yeah, of course.
So in the task-free, let's say, protocol, at least in the image, I see that up to a certain point, you don't see the 0 label anymore, right? But is this like just an example, or let's say it is indeed like slowly distribution change that does not repeat itself later on in the sequence? I don't know if the question is clear. Yeah. So I mean, so it's a very good point. So essentially, with task-free, at least the way sort of like I'm referring it to here, yeah, it just means that there are none of these task boundaries. Okay. Essentially, that the sequence could be arbitrary. Yeah. It could really be anything. So the zeros, they could appear at some later point as well. But essentially, kind of the point is, okay, like many of the existing methods, they're only applicable to this task-based class incremental learning protocol. But actually, the implementation that we proposed in this paper, it's equally well applicable to the task-free setting, because essentially each variational autoencoder model is simply only trained on the classes, on the examples from its own class. So sort of the way these classes are intermingled doesn't matter at all. But in order to be able to compare to the other sort of existing methods, the actual protocol that we use is task-based, but the results that I show for the generative classifier, they are equally valid for any task-free protocol, for any class-incremental task-free protocol, I should say. Okay, then another important difference is data storage. I already touched upon that, and essentially, well, we're only considering methods that do not store any data. So we're not allowing methods to store any data. And well, sort of the importance of this assumption is quite well appreciated in the literature. The importance of pre-training, I would argue, is maybe not always appreciated. But actually, I think it's actually a very important factor. And so therefore, sort of, well, to evaluate a diverse set of benchmarks, we considered both some benchmarks where there isn't any pre-training, so MNIST and CFAR10, and then we also considered two benchmarks where we did start with a pre-trained model on some data set. So the convolutional layers here are pre-trained on CFAR10, and the ResNet 18 is pre-trained on ImageNet. Okay, so well, so if pre-trained networks are available, how can we use them in our generative classifier setup? But essentially, the way we use them is as displayed here. So what we do, if we take the pre-trained model that is available for the particular benchmark, and we essentially use it as a feature extractor, as a fixed feature extractor, and we train our separate VE models rather than on the raw inputs. We train them directly on these extracted features. So also the reconstruction loss is in this feature space, and that is very reminiscent of these recent studies that apply generative replay in the feature space as well. Okay. So then the results, and well, yeah, I kind of apologize to just dump all of the results out there at once. I didn't really have time to structure them into a more coherent story, but
But in some way it's nice, because I think it already shows, right, that this generative classifier, this sort of like this naive implementation of a generative classifier that we used, it comfortably outperforms all of these other methods on almost all of the benchmarks. And well, now let me go through a couple of comparisons that I think are of particular interest in a bit more detail. So firstly, I think a very interesting comparison is the comparison between generative replay and generative classifier, and the generative classifier. And as I said, this comparison is fair in the sense that we ensure that that both implementations they use the same total number of parameters. But as you can see, it's the generative classifier actually outperforms generative replay and then all of the versions of generative replay on all of these benchmarks. And particularly interesting, I think, is the comparison between on CFAR 100 between the generative classifier and this brain-inspired replay, because this is the exact protocol on which brain-inspired replay. So that's a version of replay in which in which like some latent features are being replayed rather than at the input level. And so this CFAR 100 protocol, it's exactly the same protocol that was used in the paper that proposed brain-inspired replay, using the exact same pre-trained convolutional layers. And again, it's an interesting comparison because both of these approaches they make use of generative models, and essentially this comparison very strongly suggests that that it seems to be a much more efficient way to use a generative model is to actually directly use the generative model to perform generative classification rather than use the generative model to generate samples to then train a discriminative classifier with those generative samples. But this comparison is not completely fair, or it's not completely conclusive in the sense that that the generative models that were used by generative replay and by the generative classifier, they differed. So by generative the generative replay approaches, they used a single generative model which aimed to learn all of the classes, while with the generative classifier there were all of these separate generative models. But now, sort of like to do a more direct comparison between generative classification and generative replay, what we did was to take the generative model underlying our generative classifier, so all of the separate VAE models, and then generate samples from them, and then train a discriminative classifier on those generated samples from the generative model underlying the generative classifier. So this is sort of like a direct comparison whether if we have a given generative model, should we use it to directly perform generative classification, or should we use it to generate samples to then train a discriminative classifier on those generated samples. And I think, well, this comparison quite conclusively shows that it appears to be better to directly use the generative model for generative classification. Okay, and oh yeah, so especially for CFAR 10, you can see that, well, the performance of the discriminative classifier trained on samples generated by the generative model is very bad. So that kind of suggests that the samples produced or generated by the generative model are not very good. So essentially, it suggests that the generative model itself is not of very high quality. And well, for MNIST and CFAR 10, we can actually visually assess that by just generating samples and looking at them. And so these are samples from from the generative models underlying the generative classifier for MNIST. Those samples look reasonably well, and for CFAR10, and well, I think you will agree that these samples are not great. But still, the sort of like the performance of the generative classifier on CFAR10, at least from a class-incremental learning perspective, is still very good. At least substantially better than all of the methods we compared against. Okay, and then a last comparison of interest that I wanted to discuss in a bit more detail is the comparison with this method SLDA. So far I haven't talked about this method yet, but actually it's well, it was the sort of the second best performing method from our comparison, and on the core 50 dataset it even achieved very similar performance as our generative classifier. So what is SLDA? So SLDA is a method that performs incremental linear discriminant analysis to the features extracted by a fixed pre-trained deep neural network. So basically an assumption of this method appears to be that, okay, we need some pre-trained deep neural network. So well, how did we apply SLDA to MNIST and CFAR10 where there was no such pre-trained neural network? Well, basically what we did was we just said, okay, we're going to apply SLDA directly on the pixel space, and still it performs really well, right? So why does it perform so well, or relatively so well? And well, our argument is that we think it performs so well because it can be interpreted as a generative classifier. Because so what SLDA does, or what like linear discriminant analysis does, is that it learns a mean factor for each class to be learned, and a covariance matrix that's shared between all of the classes. And then implicitly, linear discriminant analysis assumes that for each class Y, the class conditional generative model is given by this normal distribution. And well, you could say that well, and SLDA is not always sort of appreciated as a generative classifier, because actually at inference time, when making a classification decision, SLDA does not need to explicitly compute or estimate the likelihoods for all of the classes, because with the assumptions it makes with the Gaussian with these distributions, it's actually possible to analytically convert a model and essentially at classification time still perform a discriminative classification. Okay. So that's sort of like our argument. Okay, why it still performs well. But the kind of the disadvantage of SLDA is that it can only learn a linear classifier. So sort of like in order to improve on SLDA, what was needed was a way to sort of like extend this in order to also be able to learn representations, to do representation learning, and that's kind of what the our naive implementation of the generative classifier was able to do, and which is why it on these three benchmarks it was able to perform better than just the linear generative classifier. Okay, and then yeah, well, very shortly, I will maybe also want to use this to make a small case for the MNIST data set, because I think it's often like people are very negative about experiments on MNIST, and that are not very useful. But I would say that actually, sort of like from all of the comparisons, the differences, they were most striking on the MNIST dataset. Sort of the comparison on the MNIST datasets in many ways that were the most informative. So I think certainly for kind of more conceptual inspired experiments, I think the MNIST dataset is very good, and it can it's very good sort of like to show examples where methods or strategies do not work. Okay, but then well, of course, there are also disadvantages of a generative classifier and also of the specific implementation of the generative classifier that we considered in the paper. And so the first of kind of the main limitations is that although training a generative classifier is relatively fast, or at least compared with generative replay, training a generative classifier is computationally less expensive. But inference, so making classification decisions with a generative classifier is computationally more expensive. And the reason for this is that a generative classifier, when it makes a classification decision, it needs to compute or estimate the likelihood for each possible class. And well, but that said, I think there are well ways to at least make this likelihood estimation a lot more efficient, or perhaps even analytically convert the model as is done in SLDA. And another way to kind of circumvent this limitation somewhat is to perhaps consider ways to make classification decisions hierarchical. For example, if we could first make the decision whether a test sample that we observe is a cat or a dog, and then in a second stage we consider on the specific breed of this of the animal. Okay, and then to briefly discuss the second limitation is it's this question. Okay, how scalable is this this approach that you proposed of simply learning a new generative model for each class? And well, of course, that's a fair argument against this specific implementation of the generative model. But I would argue that, well, in practice, there certainly needs to be some sharing between the generative models of all of the classes to be learned. And well, and this is essentially a task incremental learning problem, right? So I think a very promising direction for future research is to try to use these existing techniques from the task incremental learning literature and apply it to learning generative models in order to do generative classification for a class incremental learning problem. Okay, and then I want to finish with this, but one very short one-sentence summary and acknowledge the funding sources for this work.
Thanks, Gido, for your interesting presentation. And so maybe I can start with a question, and we read some of the questions that arrived also in the chat, and I think that this is going to trigger an interesting discussion. So with respect to the experiments in which you don't have a pre-trained feature extractor, so I'm not sure I understood how you can essentially preserve the feature extraction layer part. You know, how can avoid forgetting if you instead start from scratch?
Okay, I'm not sure I completely understood the question, but I think it's
yeah,
it's about basically about this slide, right?
Yeah. So essentially, when you learn about a new, let's say you train a new variational autoencoder, then you backpropagate also the errors through the pre-trained feature extractor. I mean, not the pre-trained. I mean the actual not pre-trained feature extractor if you don't have it.
Sorry. So this one is fixed. So the pre-trained feature extractor is fixed.
Also in the case where you don't have a pre-trained.
So in the case that there is no pre-trained feature extractor, well, there is no pre-trained. So there's so in that case, the variational autoencoder models, they're all learned on the raw inputs.
Ah, okay.
Yeah.
Okay, I get it. So oh, cool. Okay. Okay, so essentially, well, I guess if you would like to apply the same method on a, let's say, high-dimensional problem, and you don't have a pre-trained method,
yeah,
I guess you can just apply like a distillation technique or something that we already know to be working to preserve somehow the feature extraction module. And try these generative classifiers technique on top of it, right? Do you think that would work, or have you had some thoughts about it?
I mean, yes. So I think that the problem that you describe, where you have a highly complex data, like a data set with complex inputs, but you don't have any pre-trained features, and you want to do class-incremental learning. I think that's just an extremely challenging problem. So yeah, I think it will work to some extent, but it's not going to get good performance, right? But I don't think any method that does not store the data. So yeah, so I think it works to some extent, but yeah, it's just a very, very challenging problem you described.
Yeah, I totally agree with you. I was just wondering, I mean, how we could apply, let's say, this particular approach in that situation as well. But yes, yeah. Absolutely. And okay, so we have another question from Gada on the chat, and she says, thanks for these very interesting insights and ideas. I'm wondering if you compare the generative classifier with embeddings networks, which also avoid using softmax for the class incremental setting in semantic drift compensation paper. I mean, and we have a link to the paper. But yes, essentially this idea of not using softmax and a basic cross entropy loss, I guess, and just have the embeddings and maybe a clustering algorithm, something similar to just make sense of these embeddings and classify them. A new pattern based on these algorithms that do not rely on softmax, and then.
So no, I didn't. So I'm not. I should have a better look at the paper that she linked. So yeah, no, I didn't. And I mean, in some sense, the way you describe the approach, actually, it does sound to me a bit like that approach is similar to some extent to the generative classification approach in the sense that it's essentially trying to do sort of like use a similar strategy. A generative classifier is maybe a bit more, I guess, like principled from a statistical point of view, but again, I should have a better look at the paper. So yeah, so I guess the short answer is no, I didn't.
Yeah, but I do think that would be a very nice, let's say, baseline to add in case you want to extend this paper, because in a sense it would broaden, let's say, the impact of the paper, saying, okay, if you just don't focus on cross-entropy loss and softmax, then this is what you can do. And I mean, generally maybe classifiers is like a better way to do things, but there is also this other alternative. I guess it's more common of just working out a way to classify things based on embeddings and stuff like that. And yeah, so we have another comment from Liu. Could you explain a bit more the inference process? Could it be possible to replace variational encoders with autoencoders using reconstruction errors?
Yeah. So yes, you could. You certainly could, and I guess it comes a bit back to the same comment I made earlier. So yeah, it would still work pretty well, I think. And with certain autoencoders perhaps even better. But I guess what you lose is the interpretation of these values as likelihoods, really as the probability of observing this test sample under the distribution of this particular class that you learned. But yeah, so in practical terms, yes, it would certainly possible. But then, well, at least sort of like formally, it wouldn't be a classifying.
Yeah, then another thing that I was wondering is that so essentially you can, I guess, with this method preserve forgetting also because you're not actually sharing weights related to the same class. So there's the idea that if I see in let's say in this sequence of batches of experiences that you encounter over time, if I see the same class again, what I would do, if I'm correct, would be to train again a new variational autoencoder, even though you have maybe a variational autoencoder that was already able to recognize and generate back an example belonging to the same class, right?
No. So an assumption that's made here is that essentially all of the training data is labeled. So essentially, if you observe the same class again, you know it's the same class because it has the label. So yeah, you would just continue training the model that you already had for that class.
Okay, but in that case, you would actually incur in forgetting, right? If you just updated the variational autoencoder.
So okay, so you would incur forgetting if so another assumption that's essentially made in this paper is that the incremental aspect of the data is purely class incremental. But if you additionally have like domain shifts within classes, that first you observe all images of cats outside and then later all
exactly
inside, so then you get additional forgetting.
Okay.
But so if that's happening, that's what I would call sort of like the domain incremental problem, kind of on top of it. So then, I guess like the solution would be use domain incremental learning techniques to then prevent the forgetting within the generative model of that class. But
I would just a bit let's say fooled by the sequence that you showed with it, that you said it's kind of already satisfied by this approach, the one on task-free, let's say, sequence, where you actually encounter things again. And well, yes, I guess it may happen naturally that you encounter examples that are different, and maybe they cover like subspaces of the entire distribution you want to cover, right? And they don't appear again in an ID way. So that's why I was wondering if this method would work, how it could work in that setting where eventually you encounter things again and may cover just some parts of the entire distribution of that class.
Yeah. So essentially for that you would need another solution. So that's kind of for that I would say you need a domain incremental solution.
Yeah, or I guess
it can be combined with this approach.
Yes, and then also I guess that this strategy may work as well. It's just that I don't see like very efficient because you create another. We would need to create another variational autoencoder to prevent forgetting, and then at inference, I don't know how that would work, but I guess it may work.
Yeah, no. So for domain incremental learning as a solution, I don't think this is a solution or like an approach for domain incremental learning.
Thanks. Thank you so much, Guido. Do we have any more questions from the audience? Some comments, some ideas, anything? Okay, I guess no. So thank you so much, Guido, for your time and for your very interesting work. Keep the good work up, and I'll see you guys next week, where we are going to have an entire meetup, the ContinualAI meetup on continual learning at the edge. So trying to see what are the next advances and trying to bring these algorithms also to the edge and on-device training and personalization. So thank you all for joining, and I'll see you then. Bye.
Well, thanks. Bye.
And yes, Guido, if you want, you can share the slides with me so that I can upload them as well.
Yeah. I'll
Thanks.
I'll share them. Yeah.
Okay. Thanks. Bye. Have a nice weekend, guys.
Bye.